Hello everybody, welcome back. Today we're going to be starting with a new data structures topic. In particular, we're going to be talking about binary search trees. And today we're going to be giving sort of an introduction to the topic, and we're really going to try and do two things. One is to sort of motivate the types of problems that we want to be able to solve with this new data structure. And secondly, we'll talk a little bit about why the data structures we already know about are not up to this task, and why we really do need something new. So to begin with, let's talk about a few problems that you might want to solve. So one is you want to search a dictionary. You've got a dictionary and you want to find all the words that start with some given string of letters. Okay. Or similarly, you've got a bunch of emails and you'd like to find all the emails that were sent or received during a given period. Or maybe you've got a bunch of friends or a class or something and you'd like to find the other person in this class whose height is closest to yours. Now, all of these are examples of what we might call a local search problem. What you want for them is you have a data structure that stores a bunch of elements. Each of them has some key that comes from a linearly ordered set. Something like a word sorted by alphabetical order, or a date, or a height, or something like that. And we want this data structure to support some operations. Things like range search, which should return all of the elements whose keys are between two numbers x and y. Or nearest neighbors, where given another key z, you want to find the things closest to z on either side in this data structure. So, for example, if we have such a data structure storing the following numbers, if we wanted to do a range search for 5 to 12, it should return 6, 7, and 10, the three numbers that are stored that are between 5 and 12. If we want the nearest neighbors of 3, we should return 1 and 4, since those are the closest things we have to 3 on either side. Now, if we just wanted to do that, it turns out you can do it. But in practice, you really want these data structures to be dynamic. You want it to be possible to modify them. So two more operations that we would like to be able to implement are insert and delete. Insert x adds a new element with key x, and delete removes an element with key x. Fine. So, for example, we have this array. If we want to insert 3 into it, we do whatever we need to. 3 is now stored in this data structure in addition to everything else. And then we can delete 10, remove that, and we've got slightly different elements that we're storing. So just to make sure that we're on the same page, if you start with such a data structure and it's empty, and you insert 3, and then insert 8, and then insert 5, and insert 10, and then delete 8, and insert 12, and ask for the nearest neighbors of 7, what are you going to return? Well, if you figure out what the data structure stores at the end of the day, you've inserted 3, 5, 8, 10, and 12. 8 got deleted, so you've only got the other 4 left over. And you want the things closest to 7 of the remaining guys, which would be 5 and 10. So that should be the answer. Okay, so this is the data structure that we're trying to implement. What can we say about being able to do it? We've seen a bunch of data structures. Maybe one of them will work. For example, we could try implementing this by a hash table. Hash tables are good at storing and looking up elements very, very quickly. Unfortunately, they're hard to search. You can't really search for all the elements in a hash table in a given range, more or less at all. In some sense, all that a hash table lets you do is check whether or not a given element is stored there. You can't find about elements in a range. Similarly, nearest neighbors is not really a thing you can do with hash tables. But they are good at insert. Insertion into a hash table is O of 1, as is deletion. But the searching aspect doesn't work here. So maybe we need something else. Well, the next thing to try is an array. And in an array, you can do the searches, but they're a little bit slow. If you want to do a range search on an array, the best you can do is scan through the entire array, figure out which elements are in the range you want, and return those. Similarly, you have a nearest neighbors search in O of n time by scanning through the entire array, keeping track of the closest things on either side to your query, and then returning the best ones at the end. On the other hand, arrays, are, at least if they're expandable arrays, are still fine with insert and delete. To insert a new element, you just add it to the next square over at the end. To delete, you can't just remove it from the array, because then you'd leave a gap. But if you take the last element and move it over to fill the gap, once again, this delete operation is O of 1 time. Perhaps more interesting than just any array, though, is a sorted array. Here we're storing all of our elements in an array, but we're going to store them in sorted order. And the critical thing about this is it allows us to do binary search. If we want to do a range search, we can do a binary search to find the left end of the range in our array, and that takes logarithmic time. And then scan through until we hit the right end of the range that we want and return everything in the middle. So the range search here is basically log n time, at least assuming the number of things we actually want to return is small. Similarly, nearest neighbors is logarithmic time. We do a binary search to find the thing that we're looking for, and we return the elements on either side of it. Unfortunately, updates to a sorted array are hard. You can't just insert a new element at the end of the array, because the array needs to remain sorted at the end, and this will generally destroy the sorted order. If you want to insert 3, it really needs to go between 1 and 4, but you can't really do that because you can't just sort of add a new cell in the middle of an array. The only way to actually do this is you can put 3 in that plot, and then everything 4 and onwards needs to shift over 1 cell to make room. And so insertion here is O of n time, which is a lot longer than we want. Similarly, deletions are going to be hard. If you delete an element, you can't just leave a gap. You need to fill it somehow. You can't just bring an element over from one of the ends to fill the gap, because that would destroy your sorted structure. So the only way to fill the gap is to sort of take everything and shift it back over 1 in order to fill things up. And that, again, takes O of n time. The final thing to look at are linked lists. Now, here you can do a range search in O of n time. You just scan through the list and find everything in the range. Similarly, nearest neighbors are going to be O of n. Of course, linked lists insertion and deletions are very fast, O of 1, at least if you've got a doubly linked list. These things are very good. Unfortunately, our searches are slow. And even if you make this a sorted linked list, if you sort of guaranteed that everything comes in sorted order, you still can't do better than linear time for your searches, because you can't binary search a linked list, even if it's sorted, because there's no way to sort of jump to the middle of the list and sort of do comparisons. And so the moral here really is that the data structures we've seen up till this point don't work for this sort of local search data structure. And so we're going to need something new. And that's what we're going to start talking about in the next lecture.